Right. This section deals with the zeros of polynomial functions. And out of that section, we're going to be using the rational zero theorem to find possible rational zeros and also find the zeros of a polynomial function. Now, let's define what the rational zero theorem is. It's this. If you have a function, f of x is equal to a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, and so on down to a1x plus a sub 0, if that polynomial function has integer coefficients and p divided by q, where p divided by q is reduced in lowest terms, is a rational zero of f, then p will be the factor of the constant term, a sub 0, and q is going to be the factor of the leading coefficient, a sub n. That's basically what the rational theorem states. Now we're going to apply this rational theorem to find out what our possible rational zeros are, I should say. Now, to use the rational zero theorem, you're going to list all the integers that are factors of the constant term, which is your a sub 0. And then you're going to list all the integers that are factors of the leading coefficient, which is a sub n. And then finally, you'll list all the possible rational zeros by taking each factor of the constant term and divide by each factor of the leading coefficient. So I have right here the possible rational zeros will be the factors of the constant term divided by the factors of the leading coefficient. So you'll take each factor of the constant term one at a time and divide that by each factor of the leading coefficient one at a time. And we're going to look at this example here. In this case, you're going to list all the possible rational zeros of this function. F of x is equal to x cubed plus 2x squared minus 5x minus 6. Okay, now here's how we work this particular problem out. Notice on the left-hand side, I have the factors of negative 6. That's the constant term. And I list these using plus or minus symbols. Okay, now if it's easier for you, you can list them in pairs. So here for negative 6, you'll have plus or minus 1 and plus or minus 6, and then plus or minus 2 and plus or minus 3. If you get a pair of factors that repeat, then that means that you've listed all the factors of that particular number. So these are all the factors of negative 6 using plus or minus symbols. And then the factors of a sub n, which is your leading coefficient, which is here, that's an understood 1. So the factors of 1, that's just simply plus or minus 1. This one's going to be quite easy. So now the possible rational zeros will be the factors of that constant term, which is the factors of negative 6, divided by the factors of the leading coefficient, which is of course the factors of 1. And all the factors of negative 6 are listed here. Plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Each of those will be divided by the factors of 1, which is just simply plus or minus 1. Now this one's quite easy because any number divided by 1 is going to be those numbers up here. So 1 divided by 1, that's plus or minus 1. 2 divided by 1 is plus or minus 2. 3 divided by 1, that's plus or minus 3. And 6 divided by 1, that's plus or minus 6. So these represent all of the possible rational zeros for that particular function. And that's all there is to it. You're just listing all the possible rational zeros for that particular function. Another example, let's say that the leading coefficient is a number other than 1, like this one. And we want to list all the possible rational zeros of this function. F of x is equal to 4x to the 5th plus 12x to the 4th minus x minus 3. Let me show you how this one is done. On the left side, I have the factors of negative 3, which is in this case plus or minus 1 and plus or minus 3. And that's all there is for those factors of negative 3. For the factors of 4, If you list them in pairs, it'll be 1 and 4, 2 and 2. So we got plus or minus 1, plus or minus 2, plus or minus 4 as the factors of 4. And then for the possible rational zeros, that would be the factors of the constant term divided by the factors of the leading coefficient. My constant term is negative 3, so we'll have the factors of negative 3 listed here in the numerator, plus or minus 1 and plus or minus 3. That's divided by the factors of the leading coefficient, which is, of course, 4, and it's these factors here, plus or minus 1, plus or minus 2, plus or minus 4. Those are in the denominator. What I'm going to do here is take each term, each number in the numerator, divide that by each number in the denominator. So the 1 and the 3 will be divided by 1. Then 1 and 3 again will be divided by 2. Then I'll take 1 and 3, and this time will be divided by 4. So 1 divided by 1, of course, is 1, and 3 divided by 1 will be plus or minus 3. 1 divided by 1 is plus or minus 1. 3 divided by 1 is plus or minus 3. Now, these same numbers are going to be divided by plus or minus 2. 1 over 2 will be plus or minus 1/2. 3 over 2 will be plus or minus 3/2. And then these same two numbers will be divided by 4. 1 over 4 will be plus or minus 1/4. 3 over 4 will be plus or minus 3/4. So these are all the possible rational zeros of this particular polynomial function. Okay, and that's all that you're doing here is just listing all the possible rational zeros for that particular function. Now, this is going to be applicable to what I'm going to talk about on this next paper. And that's finding the zeros of a polynomial function using that rational zero theorem. The first thing you'll do is find the first rational zero by using a trial and error process that involves synthetic division. Okay. On one of the videos where we were talking about dividing polynomials, we talked about how to divide using synthetic division. That's what you'll use in this particular situation. Then next, if f of x is divided by x minus c and the remainder is 0, then we can say that that constant called c is a zero of f. And then you're going to use the result of the synthetic division to factor the original polynomial. And then you'll set each factor equal to 0 to identify any additional rational zeros. So in this case here, let's see how this is going to be done. Here we want to find all the zeros of this function. F of x is equal to x cubed plus 8x squared minus 11x minus 20. Okay. So I'm going to go ahead and write down the function here, and then you'll see how this is going to be done. This is f of x is equal to 8x cubed plus x cubed plus 8x squared plus 11x minus 20. Okay, now in this case, you want to find the factors of your constant term, which is in this case the factors of negative 20. And I like listing these in pairs. This will be plus or minus 1 and plus or minus 20, then plus or minus 2, then plus or minus 10. 3 can't go into negative 20 evenly, but 4 can. And that would be plus or minus 4 and plus or minus 5. So these are all the factors of negative 20. And then the factors of a sub n, which is my leading coefficient. In this case, that's the coefficient of the variable with the highest exponent. That's 1. And there's only plus or minus 1. Now in this case, that's quite easy because all we have to do there is just list all the possible rational zeros. And that's going to be the factors of the constant term, which is of course the factors of negative 20. divided by the factors of the leading coefficient, which is, of course, 1. Okay. And in numerical order, this will be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, plus or minus 20. Those are all the factors of negative 20, divided by the factors of 1, that's simply plus or minus 1. Okay? If I take each one of those and divide that by 1, I'm going to get all these terms in the numerator. So I can go ahead and rewrite this as plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, plus or minus 20. So those represent all the possible rational zeros of this particular function. Now, the next thing we need to do here is test each one of those using synthetic division. Okay, so we got, in this case, actually 12 possible rational zeros here because the plus or minus symbols here. What I'm going to do here is test positive 1 to see if that's a possible rational zero. So here I'm testing 1, which means 1 is going to be my divisor, and I'm using synthetic division, by the way. Now for this x cubed plus 8x plus 11x minus 20, there are no missing terms here. So the coefficient of x cubed will be 1. For x squared, that'll be 8. For x, that'll be 11. The constant is negative 20. And then we use the synthetic division process. We bring down that 1 in the bottom row. That's my leading coefficient. Then do 1 times the divisor of 1, which is 1. And then add 8 and 1, that will give you 9. And then 9 times 1, which will be 9. Then 11 plus 9, that will give me 20. And then 1 times 20, that will give me 20. Now negative 20 plus 20, that's going to give me 0. In this case, I know 1 is going to be a 0 of this polynomial function because I came up with a remainder of 0. Okay? So we know from x minus c, x minus 1 is going to be a factor of this polynomial function. The other factor is right here. And if you recall, when you rewrite your quotient, it's always one exponent less than the highest exponent in that particular function. The function started off as x cubed, so that means that this will start off as x squared, then plus 9x, plus 20. Then we're going to set that equal to 0. Okay? And then we're going to factor x squared plus 9x plus 20. So x minus 1 comes down here. We can factor x squared plus 9x plus 20 into two binomials. The factors of 20 that will give me 9x will be 4 and 5. So this will be x plus 4 here and x plus 5 here. Multiply by x plus 1, that's going to give you 0. And then we go ahead and set each binomial factor equal to 0. So we have x minus 1 is equal to 0, x plus 4 equal to 0, x plus 5 equal to 0. And then we go ahead and solve for x. For x minus 1 is equal to 0, we can say that x is equal to 1. For x plus 4 is equal to 0, that means x is equal to negative 4. And for x plus 5 is equal to 0, that means x is equal to negative 5. So 1, negative 4, and negative 5 are the solutions to this polynomial function using the concept of the rational zero theorem. Okay? And of course, that negative 4 and that negative 5 were one of my possible rational zeros here. So when I figured this out by testing 1, I did get a 0 for a remainder. So that tells me that x equals 1 is a root or solution to this equation. And I can easily use this part to find the other two. Okay. Take a look at this particular problem. Here we got x cubed. Well, f of x is equal to x cubed plus x squared minus 5x minus 2. And we want to find the zeros of this function using that rational zero theorem. Okay. So let's look at the factors of the constant term, which is in this case -2. Okay. My constant is -2, so the constant term is -2, so the factors of -2 are just simply plus or minus 1 and plus or minus 2. And then the factors of the leading coefficient, well, that's the coefficient of the variable with the highest exponent, and it's understood 1. So this one's easy. That's just simply going to be plus or minus 1. So my possible rational zeros would be this. The factors of the constant term, plus or minus 1 and plus or minus 2, divided by the factors of the leading coefficient, which is plus or minus 1. Well, divide anything by 1, you'll get what's in the numerator. So that's simply going to be plus or minus 1 and plus or minus 2 as your possible rational zeros. Okay, now we want to find out which ones are my possible rational zeros here. So in this case, I'll have to test each one of those. I have to test 1, -1, 2, and -2. Okay, I'm going to start off by testing 1. Okay, so here 1 will be the divisor. Now notice that there are no missing terms here in our f of x function. So the coefficient of x cubed is 1. For x squared, its coefficient is 1. For x, its coefficient is -5. The constant is -2. So we have to use synthetic division until we get a remainder of 0. Now if I bring down the 1 in the bottom row, multiply 1 times 1, that's going to give us 1. 1 plus 1 will give us 2. Then 2 times 1 will give us 2. -5 plus 2 will give us -3. Then -3 times 1 will be -3. -2 plus 3 is -5. Unfortunately, I did not get a remainder of 0 here. So we know that +1 would not be a 0 of this particular function. Now we have to try -1. So here I'm testing -1. So -1 would be the divisor. That 1, the 1, the 5, and the -2 are the same. 1, 1, -5, -2. And then we use the synthetic division process again. So now we bring down the 1. So 1 times -1 would give us -1. That goes here. -1 plus 1 is 0. 0 times -1 is 0. -5 plus 0 is -5. Then -5 times -1 will be +5. -2 plus 5 is 3. Again, I did not get a 0 remainder when I tested -1. So -1 would not be a root or a 0 for that polynomial function. Okay, so let's test 2. Let's test the number 2. So 2 will be the divisor, and the dividend will remain the same. 1, 1, -5, -2. In this case here, bring down the 1. 1 times 2 will be 2. And then 1 plus 2 will give us 3. 3 times 2, that will give us 6. -5 plus 6 will be 1. Then 1 times 2 will give us 2. Now -2 plus 2 is 0. Finally, we have a number that is a 0 of this particular function. So here, because I got a remainder of 0, that means that 2 is a 0 of this particular function. So I know one of the factors, because of the form x minus c, one of the factors would be x minus 2. The other factor is going to come from this quotient, which is one exponent less than the highest exponent in our polynomial function. It was x cubed, so this 1 becomes the coefficient of x squared, then plus 3x plus 3. No, plus 1, I'm sorry, equal to 0. That's x squared plus 3x plus 1 equals to 0. Now, unfortunately, we're not going to be able to factor x squared plus 3x plus 1 into two binomials because there's no factor of 1 that's going to give us a middle term of 3x. So the only alternative that we're going to have to use is the quadratic formula. Now, if I set each binomial factor equal to 0, by the way, x minus 2 is equal to 0, and then x squared plus 3x plus 1 equal to 0. Well, for x minus 2 is equal to 0, we know x is equal to 2. But this one, we're not going to be able to factor, as I mentioned earlier, so we have to use the quadratic formula. If you recall, it's this formula, x is equal to negative b plus or minus the square root of b squared minus 4ac, and all that's divided by 2 times a. And in this case, a is 1, b is 3, c is 1. And then we replace the a, the b, and the c in that quadratic formula. So here we're going to have x is equal to, let's see, negative b, b is 3, so that'd be negative 3 plus or minus the square root of b squared, or 3 squared, minus 4 times a, which is 1, times c, which is 1. And all that's over 2 times a, or 2 times 1. Now let's simplify this. Bring down the negative 3, plus or minus the square root of, well, 3 squared, that's 9, minus 4 times 1, that's simply 4, over 2 times 1, which is 2. Now 9 minus 4 will be 5, so here we're going to have x is equal to negative 3 plus or minus the square root of 5, and all that's going to be over 2. And unfortunately, that's going to be as far as we can go with that particular problem here. So in this case, my solution set, of course, x is equal to 2, so we're going to have a 2 here. Now, I'm going to break this up into negative 3 plus square root of 5 over 2. And the other factor is negative 3 minus the square root of 5 all over 2. So that part right there represents the solution set for that particular polynomial function. In fact, those are all the zeros of that particular polynomial function. Okay, so that concludes this particular section on the zeros of polynomial functions.